Now we move on to the discussion on ARMA models. ARMA stands for Autoregressive Moving Average Models. So just like we have an order for an autoregressive model and an order for a moving average model, an ARMA model has two orders. We will call it PQ, P and Q. So the P part would correspond to the order of the AR part of the model, and Q would correspond to the order of the MA part of the model. So when I get into the proper definition, you would understand what the AR part and the MA part of the model are. So as a notation, we specify an ARMA model as ARMA P, Q. If P equals 1 and Q equals 0, that would imply an ARP model. Excuse me. If P equals 2, Q equals 0, then that would be an AR2 model. And in general, if we have some arbitrary P that is greater than 0, but Q equals 0, that would become an ARP model. In a similar manner, if P is equal to 0, Q equals 1, that would imply an MA1 model. If P equals 0, Q equals 2, that would be an MA2 model. Likewise, if P is if P is equal to 0 and Q is greater than 0, then that would be an MAQ model. So by all means, an ARMA model is a generalization of a stationary time series model. And if P is greater than 0 and Q is greater than 0, we cannot specify the model as either AR or MA because it is a combination of both AR and MA. Therefore, we call the ARMA PQ model is called a mixed model. Because we have both AR, P and MAQ combined together. So, the proper definition of an ARMA model. So it has two parts. One is called the autoregressive part and the other is called the moving average part. So what we have here is xt minus phi1 xt minus 1 minus phi2 xt minus 2 minus all the way up to phi p xt minus p. And that would equal to a sub t minus theta 1 xt minus 1 minus theta 2 xt minus 2 minus all the way up to theta q xt minus q. So here, the right-hand side is called the AR part, or the ARP part, and the left-hand side is called the MAQ part. Oh, I made a mistake. Let me fix that right now. So you should have noticed that the MA models are based on the noise, so it should be A sub t, not X sub t. So that would be the MAQ part of the model. So, as an example, suppose we consider an ARMA 1-1 model. That would mean we have an AR1 model and an MA1 model mixed together. So we will have xt minus phi1 xt minus 1. That would equal to a sub t minus theta 1 a sub t minus 1. So we know that that is an AR1 model and that is an MA1 model. So AR1 and MA1. In a similar manner, we could have an ARMA 1-2 model. In other words, there is one coefficient in the AR part and there are two coefficients in the MA part, and we would have xt minus phi1 xt minus 1 equals at minus theta 1 at minus 2 minus theta 2, a sub t minus 1 theta 2 a sub t minus 2. And of course we could have a 2-1 model, which would be xt minus phi1 xt minus 1 minus phi2 xt minus 2 equals at minus theta 1 a sub t minus 1. And we can keep on going with 2-2, 2-3, 3-2. But I'm sure that you get the picture by now as to what an AR model is. Now, typically it becomes quite cumbersome to find the appropriate model, and we have to get into things called model identification, because at the end of the day, we don't want to overcomplicate a time series model. And keep in mind the principle of parsimony. So if I can get a good model with fewer number of parameters, we want to go for that model. There is no need to go for a higher order AR part and a higher order MA part in order to fit the series. What do I mean by that? As an example, Suppose a time series can be modelled using an AR3 model or an ARMA 5.2 model. So both models seem to work great, but given the two prospects, we have to ask the question, well, do the two models perform the same? If they perform in a similar manner, if the two models seem to fit the series, well, then we must choose the AR3 model. Why is that? Well, an AR3 model has three coefficients, which would be phi1, phi2, and phi3. And an ARMA 5.2 model has 7 coefficients, which should be phi1, phi2, phi3, phi4, phi5, and theta 1 and theta 2. So this is where one has to keep in mind about the principle of parsimony. Since both models give the same amount of accuracy, there is no need for us to put in more coefficients. The reason being, from a computational standpoint, the more coefficients we have, the harder the computation is going to become. And we don't want that. So if two models are going to give us the same performance and one has 3 coefficients and the other has 7 coefficients, let's go with the simpler model. Again, as I mentioned, there are model identification techniques which would help us identify the model that we want to go for. So now we have the characteristic polynomials. If you recall, we have an ARMA PQ model as xt minus phi1 xt minus 1 minus phi2 xt minus 2 minus all the way up to phi p xt minus p. And that would equal to a sub t minus theta 1 a sub t minus 1 minus theta 2 a sub t minus 2 minus all the way up to theta q a sub t minus q. Let's apply the backwards operator. We would have xt minus phi1 b times xt minus phi2 b squared times xt all the way up to b raised p xt equals at minus theta 1 b times at minus theta 2 b squared times at all the way up to theta q b raised q at. I have an xt in common on the left hand side, so I would have x sub t times 1 minus phi1b minus phi2b squared minus all the way up to phi p b raised p. and that would equal to a sub t. A sub t is in common 1 minus theta 1b minus theta 2b squared minus all the way up to theta q b raised q. So on the left hand side we have a pth degree polynomial. The right hand side we have a qth degree polynomial. And those two would be the characteristic polynomials for the AR part and MA part of the model. Going with the same notation that we use for AR models, we would have phi b or phi of b on this side, and on the other side we could have it as theta of b times at. So we simply reduce the model and write it in terms of the characteristic polynomial. So naturally the phi of b will have p roots and theta of b will have q roots. So we know conditions for stationarity with an AR model. The roots of the polynomial for an AR model must lie outside the unit circle, which would imply stationarity. There is a new condition here using the MA part. So if I rewrite the model, I could write it as so I'm going to divide both sides by theta of b. So those two would go away. And we would simply, excuse me, theta inverse b phi of b equals a sub t. So for us to write it in this manner, the denominator on the left hand side cannot equal 0. That is a simpler explanation. So in other words, that part must exist. The inverted theta b must exist. So the second condition is called invertibility. So the ARMA PQ model is invertible if the roots of theta of B lie outside the unit circle. And another note here, the roots are related to the natural frequencies. I could also call them as system frequencies. In the series. And the AR part would play a special role, and the MA part would also play a special role in terms of the series. In other words, the AR part will result in peaks in the spectrogram, whereas the MA part will result in dips in the spectrogram. What do I mean by that? So if we get the spectrogram for a series, this is an example. And we end up seeing something like this. So there is a peak there, a peak there, and there is a dip and a dip. So just by looking at this frequency graph with the spectrogram, we can sort of guess that this is an ARMA 2-2 model, because I see two peaks and technically three peaks. We have a 3-2 model. There are conditions to determine how big of a peak is reasonable to consider whether we need to keep that particular order or otherwise. Again, that gets into the concept of model identification. So finding the natural frequencies or system frequencies are quite important, because that would tell us the type of model we have. So let us consider an ARMA 1-1 model, and let's say xt minus 0.85 xt minus 1 equals a sub t minus 0.72 a sub t minus 1. So clearly here we have phi1 equals 0.85 and phi2 theta 1 equal to 0.72. In terms of the characteristic polynomial, we have xt times 1, don't want to skip a step here, xt minus 0.85 b times xt equals at minus 0.72 b times a sub t. Xt times 1 minus 0.85b would equal to at times 1 minus 0.72b. So the characteristic polynomial for the phi part is 1 minus 0.85b. The characteristic polynomial for the theta part, or the MA part, is 1 minus 0.72b. We could also write this as phi of s equals 1 minus 0.85s, and theta of s is equal to 1 minus 0.72s. So let us see if the model is stationary. So we set phi of b equal to 0, and we solve for phi of s and we solve for s. So that would mean 1 minus 0.85s would equal 0. 1 equals 0.85s, which would imply s is equal to 1 over 0.85. So s happens to be, 1.18 approximately, and that particular value lies outside the unit circle, which would imply the model is stationary. The next condition to check is the model invertible? To check for invertibility, we set theta s equal to 0 and solve for s, which would imply one minus 0.72s equal to 0, 1 would equal to 0.72s, which would imply s is equal to 1 over 0.72. and that is approximately equal to 1.39. So the root lies outside the unit circle, which would imply the model is invertible. Here is another example. Let us consider an ARMA model xt minus 0.75 xt minus 1 plus 0.4 xt minus 2 equals 80 minus 0.89 80 minus 1. Clearly this would imply that phi1 is 0.75 and phi2 equals negative 0.4, theta 1 would equal 0.89. We could rewrite the model as xt minus 0.75 b times xt plus 0.4 b squared xt equals 80 minus 0.89 b times 80. Let's pull the xt out on the left hand side. We have 1 minus 0.75b plus 0.4 b squared. On the right hand side we have 80 times 1 minus 0.89 b. So the characteristic polynomial for the AR part is phi of b excuse me, equal to 1 minus 0.75b plus 0.4 b squared, which we could also write it as phi of s equal to 1 minus 0.75s plus 0.4 s squared. Likewise, the characteristic polynomial for the MA part is theta b equal to 1 minus 0.89b. Could also write that as theta s equals 1 minus 0.89s. Is the model stationary? So we set phi of s equal to 0 and solve for s. So 1 minus 0.75s plus 0.4 s squared would equal 0. We have to use the quadratic formula because that is a second degree polynomial. So s would equal to minus b plus or minus b squared minus 4 times a times c divided by 2 times a. which would give us 0.75 plus or minus square root 0.5625 minus 1.6. Divided by 0.8. So that is 0.75 plus or minus 1.6 minus 0.5625 is 1.0375, but I reversed the order, so that would equal to I times 1.0375 divided by 0.8. So 0.75 divided by 0.8, it's 0.9375 square root of 1.0375 divided by 0.8, we have 1.273. So we look at the unit circle in the complex plane. It's the real part, the imaginary part. So that would be positive 1, negative 1, 1, and negative 1. If I plotted this, the real part here is 0.9375, the imaginary part is 1.273. So 0.9375 and 1.273, so that would be 1.273, and that the coordinate pair would be 0.9375, 1.273. So clearly that point lies outside the unit circle. Which would imply the model is stationary. Now you just have to check for one of the roots, because if the roots are complex then they occur in coordinate pairs. So if one of them lies outside the unit circle, naturally the other one would also lie outside the unit circle. Is the model invertible? So we have the characteristic polynomial for the MA part as 1 minus 0.89s. So we have to set theta s equal to 0 and solve for s. So 1 minus 0.89s would equal to 0. 1 would equal to 0.89s, which would imply s is equal to 1 over 0.89. Which would give us 1.124. And clearly that is outside the unit circle and it is a real number, so it's obvious. So we could say that the model is invertible. We can extend the idea of finding autocorrelation functions and variants of the series to ARMA models, ARMA PQ models, but it is always best to start with a simple case because things could get out of hand really fast. So I am going to find gamma naught for an ARMA 1-1 model. So we know that an ARMA 1-1 model is x sub t minus phi 1 x sub t minus 1. That would equal to a sub t minus theta 1 x sub, a sub t minus 1. So let's multiply by x sub t. So we have x sub t squared minus phi 1 x sub t times x sub t minus 1 equals x sub t at minus theta 1 a sub t minus 1 times xt. So we move that term to the right hand side. And we would quickly realize by taking expectations so the left hand side is simply gamma naught. You could bring phi 1 out, expectation of xt times xt minus 1 plus the expectation of xt times at minus theta 1 expectation of xt comma at minus 1. And we will have gamma naught equals phi 1 gamma 1 plus expectation of xt h sub t minus theta 1 expectation of xt at minus 1. If we recall, x sub t is j equals 0 to infinity psi j a sub t minus j. So that comes back from the definition of a linear filter. So which would imply gamma naught is equal to phi 1 gamma 1 plus expectation of sum j equals 0 to infinity psi j at minus j at minus theta 1 expectation of sum j equals 0 to infinity, x of t is getting replaced, so we would have psi j at minus j times at minus 1. The sum is a constant, so I could pull it out, or not a constant, but I could pull the sum out due to linearity of expectations, and I'll have expectation of at minus j times at minus theta 1 sum j equals 0 to infinity psi j expectation of at minus j and at minus 1. So the noise here can only be dependent if j is equal to 0. So in the first term, i.e. expectation of at minus j at, if j is equal to 0, then expectation of at minus 0 times at would equal to expectation of at times at, which is expectation of at squared. Expectation of at squared is simply the variance. Now, in the second term, expectation of at minus j times at minus 1, if we have j is equal to 1, then expectation of at minus 1 multiplied by at minus 1, and that we know is equal to sigma squared a. But for any other value of j, the indices will not match and the noise would be independent of time points. Therefore, it is simply going to be equal to 0. So we will have phi1 gamma 1 plus the first term is equal to sigma squared a only when j is 0, so we have psi 0 sigma squared a. The second term is equal to sigma squared a only when j is equal to 1, so we have theta 1 psi 1 sigma squared a. Therefore, the variance of the series is phi1 gamma 1 plus psi naught sigma squared a, sigma squared a times psi naught minus theta 1 psi 1.